So, good afternoon. My name is Bert Hoffman, and it's a great pleasure for me to welcome you at this seminar in the series of the Department of Epidemiology of the Harvard School of Public Health. And it's a great pleasure for me to introduce, truly a great pleasure, I must say, to introduce Dr. Timothy Lash, who is our speaker of today. Dr. Lash is the O. Wayne Rollins Distinguished Professor of Epidemiology and Chair of the Department of Epidemiology of Emory School of Public Health. And he focuses in terms of substantive research on cancer. Um, but I think we know him particularly in epidemiology because of his great contributions in epidemiologic methods, looking at quantification of the various types of bias that we have in epidemiology. And that is, Tim, what you're going to talk about today. Quantitative bias analysis, the good, the bad, and the ugly. Dr. Tim Lash, please take the floor, and thank you for being with us.
Thank you, Bert. It's very nice to be here. Wonderful to see so many friends at Harvard, and I should also say thank you for accommodating my reschedule from last year. I truly
Happy
appreciate
to
it.
do so. Happy to do so. Wonderful that you're here.
Let's see. I'll share slides. Okay. So, today I'm talking a little bit about bias analysis and especially about misclassification. This is a statement of the objective as I see it, which is a valid and precise and generalizable or transportable measure of the occurrence of disease, if we're talking about descriptive epidemiology, or the effect of an exposure on the occurrence of disease, if we're talking about etiologic epidemiology. And the first thing, of course, is that the objective has three characteristics. Valid goes to systematic error, precise goes to random error, and generalizable or transportable goes to representativeness. But maybe the most important thing is that this is a measure. It's science, it's an exercise in measurement, and all measures are imperfect. And so the premise is that since our objective is a measurement with these qualities, then we have an obligation to quantify how far from that objective we might have fallen. And conventionally, we do a pretty good job of this when it comes to random error. The things that you're familiar with that quantify the role of chance, confidence intervals, p-values, only quantify chance. And if you look at their definitions, require an assumption of no bias acting on the adjusted estimate. However, we do not ordinarily quantify systematic errors, even though these errors oftentimes dominate the uncertainty, especially in this era of ever-growing study sizes and large administrative databases and so forth. So the good of quantitative bias analysis is that it does this. It measures systematic error, measures the direction, size, and uncertainty from systematic errors. And when I talk about quantitative bias analysis, I use it as an umbrella term, meaning anything that accomplishes that goal. So missing data methods, for example, I would consider quantitative bias analysis. Some of the work that Donna Spiegelman has done when she was at Harvard falls in this regression calibration, and then the kind of things that I'll talk about today, which are more simulation-based methods. So here's just a very simple example. Imagine that we start with the study with a true null effect in the top left-hand corner. It's 1,000 people. There is no effect of the exposure on the outcome. But then imagine that not everybody that we would like to have in the study agrees to participate. And so the participation proportions are in the lower left-hand column, and you can see that they are differential. The proportion participating depends on both the exposure and the outcome. And so what you expect to observe then is the table in the top right-hand corner where the association is not null. It's it's 1.3, not 1. And the difference between 1.3 and 1 is due to systematic error, not chance. And so we can recover an estimate of the unbiased estimate using a bias model. And bias model just is a model that connects the estimate, the OR with the hat over it, with the unbiased estimates, here OR sub true, as a function of bias. And then that bias is a function of bias parameters. And here, those bias parameters are just the 4 selection proportions in the bottom left-hand corner. And so, with a little bit of rearrangement, you can recover an estimate of the truth. And here, that's just algebra, you know how to do that. And so it all works quite well. The challenge is always going to be that the values to assign to the bias parameters are not known. They're not identifiable. And, here we know them because I made them up and told them to you. But if we take the, what would actually happen, we would have a study with, for example, 130 of 200 participating cases. So we know the marginal participation rate is 65%, but we need the interior participation rates of 70% and 60% to recover the truth. And you're not going to know that because you need people to participate in the study in order to learn their exposure status. And so you can bound it, you can estimate it, but you are never going to know for sure the values to assign to the bias parameters. And that is the fundamental challenge of any bias analysis problem, is what values to assign to the bias parameters. We're going to be talking about exposure misclassification, which kind of has similar format. We can start with a table with the true cohort data, and then what we expect to observe is a function of the sensitivities and specificities of exposure classification. Or we could go the other way around and start with an observation, and with just a little algebraic rearrangement, we can get what we would call the bias-adjusted estimate, and we would use estimates of the sensitivities and specificities to calculate that bias-adjusted estimate. And those estimates of sensitivity and specificity could come from some other study, it could come from an internal sub-study, it could come from your educated guesses. Now I want to spend just a minute to talk about the importance of specificity, because when it comes to these misclassification problems, sensitivity and specificity seem like they might be equivalent, but actually the strength of bias is almost always determined by the specificity. And that's for when the exposure is rare or when the outcome is rare. Misclassification is driven by specificity. And so here's a little cartoon to illustrate that. Let's imagine a cohort where the exposure prevalence is 10%, and that's illustrated by the narrow blue bar, and the unexposed group then is 90%, and that's illustrated by the wide red bar. And the risk in the exposed is twice that in the unexposed, which you can see by it being twice as tall. Now, when we misclassify the exposure by having, say, sensitivity of 90% and retaining the specificity at 100%, what happens is that 10% of that narrow blue bar gets moved over and joins the wide red bar. And you can see then that what we measure as the risk in the unexposed is a weighted average of that thin blue slice with the very wide red slice. So it really has almost no consequence. And you end up with a risk difference that should have been 0.01, and instead you'll get 0.00989, like very close to the truth. And that's so this 10% sensitivity has almost no biasing effect. On the other hand, when you take specificity of 90%, you move 10% of the wide red bar and it joins the narrow blue bar. And so the signal to noise ratio in the exposed then becomes like 50-50, 50% signal, 50% noise. And you get this very large impact on the estimate of risk in the exposed, which leads to a very large bias in the risk difference. It's reduced by almost half. And so specificity of 90% when the exposure prevalence is low has a very different consequence than sensitivity of 90%. And that's because the exposure is rare. And of course, when both are misclassified, you have the same kind of effect, but most of the bias is still coming from the poor specificity. Okay, so as I alluded to earlier, the bad of bias analysis is that we will never know the values to assign to the bias parameters of the bias model with certainty. And I'm going to illustrate that consequence of that using an example from a case control study from 2006 done by colleagues at Group Health. And their research question was to evaluate the association between use of antidepressants and breast cancer risk. This was a population-based case control study. The source population included women 65 to 79 living in one of 3 western Washington counties between 1997 and 1999. Cases were identified by the Population-Based Cancer Registry. They're one of the SEER registries. And then controls were matched to cases using Medicare data. That's why the population was limited to people 65 and older. And then the history of antidepressant use and other exposures was ascertained by an in-person interview with both cases and controls. And they were asked about their 20-year history of antidepressant use. And so the result in the paper was an odds ratio of 1.2 with 95% confidence interval 0.9 to 1.6, which the authors described as showing no association between every use of antidepressants and breast cancer risk. This is the 2x2 table. This is unmatched and uncontrolled for confounders. And what you can see is that the crude odds ratio is almost identical to the reported adjusted odds ratio, adjusted for what they viewed as a sufficient set of confounders and adjusted for the matched factors. And so I show you this really only to illustrate that we don't really have to worry about confounding. It appears we can just use the 2x2 table for our misclassification problem. And the other thing that I want to point out to you is that the history of ever antidepressant use in the preceding 20 years is rare. And if we look in the controls, it's pretty close to 10% of controls had a history of antidepressant use. So that's the exposure prevalence. And since the exposure is rare, if it has been misclassified, the strength of bias we know would be driven by specificity. And so a question to ask is whether the null result, or what was interpreted as a null result, could be due to misclassification of self-reported antidepressant use. Now, the authors knew that self-reported medication use might be misreported, and so they conducted and reported an internal validation study. And, all credit to them for conducting a validation study. I think this is an underappreciated skill in epidemiology. The design and implementation of validation studies is, I think, underappreciated. There are nuances to it that are complicated to get the most information out of the limited resources that can be allocated to a validation study. So I want to start by giving them all credit for having done this. And what they did was to compare the interview report of antidepressant use with the pharmacy record. These are electronic records of pharmacies. And so participants were restricted to people who said that they filled their prescriptions at the same pharmacy for a long period of time, and where those pharmacies had electronic records of filled prescriptions. And people had to consent to a second aspect of the study, which was participation in the validation study. So, like any validation study, there are uncertainties and biases in the validation study that parallel some of the things we worry about in the parent study. So with that said, here among cases is the comparison of 2-year pharmacy record, because they didn't have electronic pharmacy records that went back 20 years, with the interview. And what they observed in cases was a sensitivity of 56% and a specificity of 99%. So what that means is that among people whose pharmacy records said they had been prescribed an antidepressant, about half had reported on the interview that they had. Now that might be what you would expect. Unfortunately, antidepressant use might be viewed as a stigmatized medical history, so it's not surprising that not everybody would report it. In addition, not everybody understands the complete set of indications for which they've been prescribed medicines. So you get this kind of sensitivity. It's not surprising. On the other hand, among women who had never been prescribed an antidepressant in the pharmacy records, 99% had correctly reported that they had been not prescribed an antidepressant. So that's also what you kind of would expect. The false positive rate is only 1%. Now, the design of this study is what I would call retrospective. Cases and controls were enrolled, and then the information about their exposure was recorded after the disease had already occurred, which means that the accuracy of reporting might be influenced by the disease itself. Cases having reasons to report their medical history differently than controls by virtue of having this breast cancer diagnosis. And so the validation data, again, to their credit, were collected and stratified by case and control status. So these are the sensitivities and specificities in cases, and these are the sensitivities and specificities in controls. About the same. 58% instead of 56%, 97% instead of 99%. You could look at this and think, well, those are pretty similar estimates. It may be that this retrospective concern is not that important, that the potential for recall bias is low given that the sensitivities and specificities are very close to each other in cases and controls. So we can take this validation data, and if we assume that the sensitivities and specificities come from the same underlying distribution, and just set the sensitivity to the midpoint of 57% and the specificity to the midpoint of 98%, that in combination with our observed 2x2 table allow us to calculate this bias adjusted or expected true estimate, and it's 1.3, a little bit further from the null, as you would expect after bias adjustment for non-differential exposure misclassification. But that's just one set of estimates. You could think about doing a sensitivity analysis of the bias analysis by assigning different combinations of sensitivities and specificities to cases and controls. And so here's one multi-dimensional table that you could create where sensitivities were either 0.5 or 0.6 and specificities were either 0.95 or 1. And then each of the values in the lower right part of the table are bias adjusted estimates calculated, in the same way using the same bias model with the different sets of assumptions. And there's lots of things that you could glean from that table, but one of them is that the range in the table, so if we think that these are reasonable characterizations of the uncertainty about the sensitivity and specificity, the range of bias adjusted estimates is from 0.86 to 1.98, which is wider than the conventional 95% confidence interval. That was 0.92 to 1.61. So one of the things that this tells me is that the uncertainty in this study emanating from exposure misclassification is as great as the uncertainty due to random error. But we don't ordinarily make these calculations, right? So that would ordinarily not be quantified for our consideration. Now these multidimensional tables are nice because they can, show you this kind of pattern, but they take a lot of text, hard to explain. Maybe more importantly, each of the bias adjusted estimates in the table appear to have the same credibility. There's no central tendency, there's no histogram or picture of the frequency distribution of the bias adjusted estimates. So there's no equivalent to the 95% confidence interval that you would get for quantifying just random error. So what you can do instead is simulation, probabilistic bias analysis, where instead of assigning one set of values to the bias parameter or 24 sets of values to the bias parameters, you assign probability distributions to the sensitivities and specificities. You then draw from those distributions and accumulate the results, which generates a histogram. The median is the central tendency, the 2.5 percentile and the 97.5 percentile of the histogram tells you the simulation interval. You can also then simultaneously incorporate random error with some resampling so that you have an interval that shows the total uncertainty, not just random error, not just systematic error, but under the bias model, the total error. So the goal here is that with some reasonable estimate of the range of values for the bias parameters, we can define distributions that reflect our uncertainty in the bias. And then use that to describe the entirety of the bias that we're worried about. If you're working with summary data, just 2x2 tables and simple distributions, you can do this in Excel. Matt Fox has written a number of Excel spreadsheets which you can freely download from our book's website. It will do bias analysis for misclassification problems, selection bias problems, uncontrolled confounding. But if you want to use record level data or more sophisticated methods, you would need to do this in R or SAS, or there are built-in algorithms now in R, in Stata, some in SAS, macros that do bias adjustment for you. So the tools are freely available. So here is using Matt's spreadsheet and using the validation data as observed to assign beta distributions to the sensitivities and specificities. And the beta distributions are on the right-hand side, and you can see the sensitivities, which relied on sort of 30-something participants, are wide, centered on about 56%, 57%, and with a lot of overlapping area under the curve. The specificities, based on more than 100 participants each, have much narrower distributions and are way to the right because they were 97% and 99%. And in fact, there is a good amount of area that does not overlap under the two beta distributions for the specificity. So although our intuition might be that 97% and 99% are not that different from each other, there is enough data to suggest that those two specificity values are different from each other, which would be allowed under the retrospective design. So then if you look at the table, the conventional result, the result I've been showing you from the start, there's the odds ratio of 1.22. And then when we bias adjust, we get a point estimate of about 1.67, with an interval accounting for both random error and the uncertainty in the misclassification, the sensitivities and specificities beta distributions, ranging from 0.9 to 4.24. Now, in the world of breast cancer epidemiology, a estimate of 1.7, that's not a null effect. Like, that's the same size as moderate alcohol consumption in relation to breast cancer risk. And so remember that the original author's interpretation was that there was no association. But when we bias adjust for the validation data as observed, using beta distributions informed only by the validation data, we get an estimate that is, to me, not suggestive of no association. And so that brings us to the ugly. And because these methods are not familiar to us, it is possible for there to be errors and even manipulation of bias analysis. And so it turns out that in the original paper, the authors did a bias adjustment. They bias adjusted for the sensitivities and specificities that were reported in the Boudreau paper. They said, using the sensitivities and specificities from the 6, 2-year, and 8-year look-back periods, the calculated odds ratios for every antidepressant use in breast cancer were 1, 1.2, and 1.2, which are similar to the estimated odds ratio that I've been showing you, the conventional estimate of 1.2. And they conclude, therefore, the importance of recall bias may be limited. Now, I showed you 1.7, and they're showing you 1.2 with bias adjustment. So what happened? Like, how did they get 1.2 from their bias model and I'm getting 1.7 from my bias model? Well, when you look at what they described, their description of the Boudreau validation study says, here are the sensitivity results, and that yellow highlighted row is the sensitivities with the 2-year look back. There's the 56% that I showed you and the 58% that I showed you. These were in the Chen et al. Paper, the same table. Now, then they say specificity estimates tended to approach or equal 100% for all time periods, regardless of which look-back period or pharmacy records you used. And the sensitivity and specificity estimates were similar between cases and controls, suggesting that they assumed non-differential misclassification. So that is how they got the 1.2. But if you go and look at their Boudreau paper, the 56 and 58, this is now the Boudreau validation study that I've been showing you, highlighted in yellow, the specificity is 99 in cases and 97 in controls, which I showed you, not 100%. In a second table, different group of participants in the validation study, in the 2-year look-back period, you can find specificity of 100 in cases and 100 in controls. But then the sensitivity is 61 and 54, not the 56 and 58 that Chen et al. Showed in their paper. In short, there is no table in Boudreau that has sensitivity of 56 and 58 and specificity of 100 and 100. Meaning that to combine those together and get the 1.2, you would have to take data from two different participant groups. And so I think that's what happened, right? If you take the conventional result, which kind of implicitly assumes no exposure misclassification, you get the conventional result of 1.22. If you take the non-differential setting that I showed you originally, you get 1.29. If you use the validation data exactly as reported, you get bias-adjusted odds ratio of 1.68. And if you use sensitivities of 56 and 58 and specificities of 100 and 100, which is what they suggest they use, that's where you get their bias-adjusted estimate of 1.1. But that set of validation results was never reported in the Boudreau paper. So, I also just want to show you quickly that if you don't like simulation, you can actually use direct bias modeling or empirical bias modeling using a method that goes back to 1988, paper written by Sander. Matt Fox has implemented it in a spreadsheet, and what you see is that the estimate is 1.63 and the interval is 0.76 to 3.47. For the sake of time, we'll go through. So, where does this leave us? If we fix the sensitivities and specificities 100%, which is basically ignoring exposure misclassification, we have our conventional result of 1.22 with interval 0.92 to 1.61. If we use simulation or the Greenland method, the bias-adjusted result is 1.63, and the intervals are, wider, taking account now of the uncertainty from exposure misclassification as well. And the main takeaway for me is to remember Chen et al.'s two main conclusions. No association between ever use of antidepressants and breast cancer risk, and the importance of recall bias may be limited. To me, these were the two central conclusions of the Chen et al. Paper. And when you use the validation data exactly as reported, neither one of those stands up. There's an association of 1.7 with interval 0.9 to 4.2, which in the world of breast cancer epidemiology, I think would not be viewed as null. And that change from 1.2 to 1.7 really is driven by this very small difference in specificity between 0.97 and 0.98, or 0.99, 0.97 and 0.99, which to our eye looks like those might be the same, but in fact, when you look at the distributions, there's a good amount of the area under the curve that doesn't overlap. And so the design, because it's retrospective, allows for differential exposure misclassification, and the validation data are consistent with a difference in specificity. And when you take that into account, you get this bias, strong bias, away from the null, all the way up to 1.7. If you treat it as equivalent, say, assign 0.98, or as if the specificity was perfect, so assign 100% specificity to both, then you get results that are not biased. So the whole thing turns on what values you assign to the specificity, and they are very close together. This is just an example of what I think, I don't know, and I know that some of these people well. I think they're terrific cancer epidemiologists. But there is always the potential for what I would call results-driven bias analysis, right? Which would be a misuse of the method. Because if you choose values to assign to the bias parameters that give you the answer you want, that is not the way we should be doing bias analysis. I don't know that that's what they've done here, but there are aspects of it that suggest that might have happened. And then you have given false assurance against the validity concern of your measure, which is counterproductive, in fact, as opposed to just having it absent altogether. And that is, where the ugly comes from. Now, I'll close by saying the real solution here is to recognize that there's a great deal of uncertainty from this study emanating from exposure misclassification. And the right thing to do is to use the bias analysis, regardless of what results you obtain from it, to identify that that is a major source of uncertainty. And the next step should be a better study where better is better exposure information and a prospective design, so you don't have to worry about this differential misclassification. Those studies have been done, including in studies of cohorts in your premier institution, and they are null. So I don't want anybody to leave here thinking that antidepressant use is associated with breast cancer risk. I don't think it is, but I don't think it is not based on this study, but based on the prospective, well-conducted cohort studies that came later. So I will then close by thanking all of the people who've helped me for many years with my understanding of bias analysis and topics like this. And I can stop here and happy to take questions or discussion.
Dr. Lash, thank you very, very much. Very great illustration of the biases that we can still keep even after analysis for it. Perhaps you can unshare if you wish, that we can see each other.
There we go.
Thank you. Wonderful presentation, by the way. Thank you for the plug for validation studies. Yes, that was good that they did that, but also sobering that a specificity of 99% or 97% has such a big effect still in terms of misclassification. Quite remarkable, I thought. I wouldn't have expected that, to be honest.
Yeah.
So thank you very, very much. I have one question in the chat, and I will give the floor there and invite others to come in and ask their questions either directly or so. The seminar is recorded, as Beth Williams has said, and the Q&A as well. If you do not want your question to be recorded, then don't ask it. So please, Rima Obiet. Rima, would you ask your question yourself, the one you put in the chat? Let me
Yes,
see.
thank you very much.
Thank you. Yeah.
My question is if the direction of bias due to differential exposure misclassification have the same direction all the time, or is the direction predictable?
Yes. So when let's do the complete thing. If there's only one variable that's being misclassified, and it is the exposure, and it has only two levels, and the misclassification is non-differential, then we expect the bias will be towards the null. You can have chance deviation from what you expect. That probability grows smaller as the study gets larger, but the bias is towards the null. When you have differential exposure misclassification, you have an unpredictable direction of the bias.
Yeah.
It may still be towards the null, but you need to know more. You need to know the sensitivities and specificities to have to do this kind of bias adjustment and work out what the expected direction would be. So a value of non-differential misclassification is the directions, the expected direction, without having to do more. Differential exposure misclassification can still bias towards the null. You just don't know until you've done the math.
Thank you.
And I think that's important because I think there is kind of this, it's easy to think that differential misclassification, this kind of recall bias, will always bias towards the null or away from the null, but that is not true. So I'm glad you raised that.
I have a question in the chat from Tyler Vanderwille, and Tyler cannot be on audio, so I understand. So I will read his question. And first of all, praise for your talk, Tim. In light of the Janet All example and other experiences you have with bias analyses, to what extent do you think responsibility for thoughtful, insightful, and probing bias analyses lies with the authors, with reviewers, and with editors? Do you think a set of best practice principles could be proposed for each?
Yeah, that's a great question. So we have published a paper on good practices for bias analysis that's directed towards what I guess would be the authors, the analysts and authors. That was published in IJE probably, 15 years ago now. So Bert, not in your journal and also not in Epidemiology.
That was a mistake, but don't worry about that further. Yeah.
And I do think that it's got to start with that, the practitioners. And none of it's really a surprise. I think, you can see some of the things that went wrong, if you want to call it going wrong, in the Chen et al. Paper. They never clearly told us what values they used for the specificity, right? Like that starts with that. And so we don't really know what values they assigned. And although they cited the Boudreau et al. Paper with the validation data, they only showed the table for the sensitivities. They didn't show us the table for the specificities. And so that kind of transparency is just good practice for any analysis, right? Like if you are using values that somebody else published, you should be very clear about which ones you're using and why. It's helpful to show in the text or in a supplement an example calculation, because then people can follow, this was the bias model, because I will tell you that they cited a paper for their bias model, and we have never been able to completely replicate their result, right? So showing the actual equation for the bias model, ideally with the values assigned to the bias parameters shown, then you can follow the calculation, right? That's just good, transparent work. And I think those are just some of the good practices. You're right, though, that peer reviewers and editors are key to this. And we've made this case in some of the things that we've written, that until it becomes the cultural norm, the social norm in epidemiology to include quantitative bias analysis, things are not going to get better. If this is better, I think it's better, but you may not agree. But until there's demand for it, I don't see it really becoming the norm. And so it is, I think, reviewers and editors, and probably mostly editors, saying that if you want to publish in our journal, you have identified in your discussion section this limitation, this uncontrolled confounder, this mismeasurement problem. Uh, do something quantitative about it. And until that becomes the cultural norm, it's not going to become, it's not going to get better. And until it gets to be the cultural norm, it's going to be hard for most of us to evaluate the bias analyses that we see and judge whether they were well done, right? Like and then that opens the possibility for manipulation, because recognize what happened here is they put up this shield saying, we know by design you were worried about recall bias, so were we. Don't worry about it. It didn't change the estimate.
No.
And so as a reviewer or an editor or a reader, you would think, oh, here's this thing that was my major concern about the study, and they've shown me that I shouldn't be worried about it. And it takes a nerd like me to go back and actually follow every step of the path and say, wait, this doesn't actually work out. No, you can't really expect everyone's going to do that.
Yeah. Thank you. I have two other questions in the chat. First, I would like to go to Debesis Paul. Yes, Debesis, would you want to ask the question yourself? If not, let me do this. In the probability, it's a straight question, Tim, to you. In the
Yeah,
probability extension
probability
spreadsheet,
is,
what
let's
kind
see.
of... Oh, yeah, please go ahead, Debasis.
So what kinds of distribution has been followed here?
This was just a beta distribution, two parameters, alpha and beta.
I mean, it's
And
a first kind or second kind, whatever.
I'm sorry, say again.
I mean, it's like a first kind beta or second kind beta.
I'm not
There
sure
are
I know
two
the
kinds of
difference.
beta distribution.
I only know one beta distribution. So it was the first kind.
Have to figure out. Okay, I have now I see hands. Benjamin Ackerman, please go ahead.
Yeah. Can you hear me?
Yes.
Cool. Um, First, thanks for a really great talk. So I'm a biostatistician by training. I work in drug development, and it's interesting. These approaches have been working their way into like regulatory guidance documents around using retrospective EHR data or, real world data in regulatory submissions and in drug development in general. One struggle I encounter regularly when using retrospective data, especially like derived from electronic health records, are challenges both in like, can a validation study ever be conducted, whether based on the data availability or even like the sort of scientific question or disease area. And then also, if not, sort of where to build intuition around constructing bias parameters or setting distributions. So I guess I'm wondering, you gave some really great examples and principles of, how to rely on literature or how to use simulation. I'm curious your thoughts on, when you're using data that are just already collected in there, and there's this broad question of we think there's exposure or misclassification, but we really have no idea how much, sort of, how would you suggest going about um, either setting some bounds or being principled in laying out where to start a bias analysis?
Yeah, great question. So um, I've done some work on outcome misclassification in real world data in a non-inferiority setting where, so it's a fascinating problem because the non-differential outcome misclassification would bias towards the null and potentially show you a false equivalency, right? Because it looks like you have a non-inferiority result, but it's emanating from outcome misclassification, and counter to what you would want as a regulator. And so, um, and you're right that in that setting, the strength of bias again is driven by outcome misclassification and specificity in particular, which is really hard to validate, right? Because you need to show that 10,000 people without the disease actually don't have the disease. Like, how are you going to do that, right? So, yes, but you can make an effort at it, right, by EMR review or clinical adjudication in some like very like have the physician's health study and nurse's health study where you have access to ancillary information that would help you to make the case that this person was never diagnosed with the condition, right? So, but if you get to the place where you really can't collect the validation data that would be productive, I think you still have to make your educated guess at it and say, or a sensitivity analysis and say it would have to be this bad before our inference would change. And that's useful, right? Because then you're quantifying uncertainty, and the alternative is to say, well, exposure misclassification or outcome misclassification might have been a problem. It would be impossible or too hard to do the validation study. So what? So then you ignore it? Like, can you grant yourself that privilege? I don't know. So
Some people do it, but I would say
yeah,
no.
but so I think that then you're in this realm, and this is all fundamentally a non-identifiability problem, right? And so like that's where I started. Is you're never going to know what values to assign here, and so what you want to do then is make the best possible inference, which I think includes a clear statement of the residual uncertainty, however you want to. And ideally that is quantified, because whenever it is left unquantified, the qualitative description of that uncertainty, in my experience, just maps with the person's prior. Right? So yeah, there's no value add then.
Thank you. We go to
Cool.
perhaps
Thanks.
Yeah.
final question. Thank you, Benjamin. Final question, perhaps Maya Petkova. Please, Maya, please go ahead. But you have to unmute yourself, probably. Yeah. There you are.
So much for the clear presentation. And I was wondering, so in your example, that really made it clear, specificity dominates because the exposure is rare in the case control design. So I was just wondering, how would that translate to a cohort study with a rare exposure? And would then specificity again be the primary driver of bias? And particularly, what are the specifics there? And what happens if the denominator is not fixed? So if it's an open cohort.
Yeah. Great questions. The fundamentals are the same. If you're dealing with an exposure misclassification problem and the exposure is rare in the cohort, the strength of bias will still be driven by specificity. And if it is an open cohort, so you have, I think what you're talking about is basically person time data. Great question, hard problem. Exposure misclassification of time varying exposures is not well worked out. So like there's an open topic for someone to do better on.
Oh, great. Thank you. Good to know.
Yeah.
Tim, thank you very, very much. I echo many comments in the chat that thank you very, very much for a great presentation. I shared it very much. It was wonderful. Very, very great illustration of a major, may I say, a major challenge we have in epidemiology. And I agree that both reviewers and editors have to do something perhaps about it. Change the culture. Thank you very much.
Thanks for having me.
Before I go away, I would like to invite you and all here to our next seminar, which will be in 2 weeks, same time, same place. It will be Alfredo Morabia. Alfredo will speak about what if. public health had to be built from scratch, which is, given the current situation in our country, not impossible. What if public health had to be built from scratch, revisiting the 19th century debates? Look very much forward to that. But I end again, Dr. Lash, thanking you very, very much for a great presentation, and everybody else for being here and asking questions. Many
That's a great
thanks.
topic,
See
and
you again.
Alfredo's a great speaker, so I hope you all go to that.
Yeah, I agree with that. Thank you, Tim. Bye bye now.